So vanishing gradient problem. So we saw that pre-deep learning era, the two most important activation functions were sigmoid and tanh. Sigmoid and tanh. So what are activation functions? The functions which are there in these neurons, right? So these functions F11, F12, all these functions, they are activation functions which are there in the neuron. So we apply these activation functions on the sum which takes place in this neuron, right? And the result of applying this activation function is the output of this neuron, right? Okay, so what we do in the back propagation phase or backward propagation phase of this training of this neural network. So we take the derivatives of loss with respect to weight. For example, if I want to update weight W11, so what is the formula? The formula is W111 new is equal to W111 old minus eta times learning rate times the derivative of loss with respect to W111 old. Right? That means we need to compute the derivative of loss with respect to the weight which I want to update. So let's say I want to update this W11. So I need to compute this derivative. So this derivative, if I write it is like this, derivative of loss with respect to weight is equal to, by using chain rule, derivative of this loss with respect to this O31 and derivative of O31 with respect to this W11. Now that's what I wrote here. Now this derivative, right? To compute this derivative of O31 with respect to W11, we have two paths. The first path is coming like this, and this is the second path, right? So let me take different color just to avoid the confusion. So this is the first path coming here, and this is the second path. These two parallel paths are coming from W111 to O31. So that's why while computing this derivative, the derivative of this path, which is this derivative, plus the derivative of this path, which is this derivative. So now the important point to note is we are taking the derivatives of these outputs. So derivatives of outputs is nothing but derivative of this activation function, because what is this output? This output is the result of applying the activation function on the sum. So for example, if I talk about this derivative, if I rewrite this derivative here, this derivative is nothing but derivative of sigma of some sum here, the sum which is coming here with respect to O to 1. Right? So that means we are ultimately taking the derivative of the sigma. Right? So, and I'm assuming the activation functions here are sigmoid activation functions. They can be tanh also, because pre-deep learning there were only two popular activation functions, sigmoid and tanh. So if I assume these are sigmoid activation functions, we are taking the derivatives of sigmoid activation functions. Right? So this is also a derivative of sigmoid. This is also a derivative of sigmoid, a derivative of sigmoid, sigmoid, and sigmoid. Right? Now let us assume here. Let's say this is point 2. Let's say this is point uh, 1. Let's say, and this is point 0.05. Right? So if I take the multiplication of these two, this will be 0.001, right? If I take them, because we are multiplying these derivatives here, right? So this will be 0.001. Similarly, if I assume some value here, again the derivative of sigmoid is less than 1, so it's a fraction of this kind, right? So again we'll get some fraction here and some fraction for this. So what will be the derivative? So let me just write the value approximately for this again, right? So it will be, let's say, 0.0001, right? I'm assuming I'm taking the product of this plus product of this into this, right? So let's say I get this value. I'll get not exact this, but I'll get this kind of value with these three zeros after the decimal point, right? So now if I write and if I update this weight, now let's take W111 old as let's say 1.5, right? It can be any random value because we have random initializations of the weights. Let's say this was 1.5 minus, let's assume this learning rate as 1 into this 0.0001, right? So if I do this, so this is multiplication between this, because this eta into this, right? So 1 into this term is this one. So this will be 1.4999, right? So this is what W new we get, W111 new we get, right? And what is this? If I consider the rounding of error, so if it will be nothing but 1.5. So old W was also 1.5, new W is also 1.5. That means there is no update in the weight. There is no update in the weight. Weights are not getting updated. They are exactly, new weight is exactly similar to old weight. So there are no updates. And why this is happening? So if the weights are not updated, the neural network will not learn. The neural network will not be trained, right? So why this is happening? This is happening because we are multiplying a lot of fractions here, lot of fractions. So these fractions we are multiplying, a lot of fractions we are multiplying, values less than 1, right? So these values we are multiplying. And what are these values? These values are nothing but derivatives of this sigmoid. So that means, and the derivative of sigmoid are less than 1. So this problem is occurring because the derivatives of sigmoid or the activation functions are fraction values like this, right? So because of this, the weights are not getting updated. Such a problem is called as vanishing gradient problem, where we are not able to update weights because of the smaller derivative values of this activation function. And that's why we'll not be able to train these neural. Imagine this is the neural network with only 2 hidden layers. Imagine what will happen if there are more hidden layers like 15, 20, right? So if there are more hidden layers like 15, 20, we'll get a value, we'll be multiplying such, let's say 50, if we have 15 hidden layers, we'll be multiplying uh, such 16 values, I guess, 16 fractions. So what will we get? 0.0000, right? So there will be no update in the weight, right? Weight. So such a problem is occurring because of this sigmoid activation function, or even if you take tan H also has similar problem. So that's why neural network were not getting trained. Deep neural network were not getting trained. So people were not able to train deep neural network because of this problem, vanishing gradient problem. So that's why people lost interest in the deep neural networks. And now, after advent of this ReLU overcomes this problem, vanishing gradient problem. But this was the problem pre-deep learning era, or at the time when people used to have this sigmoid or tan H as activation function, right? So this was vanishing gradient problem. If I write the problem in a nutshell, we multiply lot of derivatives of sigmoid. That means, that is, we multiplied like values like zero point 0.2, zero point 0.1, 0.05, 0.003, etc. A lot of these fractions we multiplied. So the W new is exactly similar to W old, right? No updates in the weights. No update means no training of the weights, no training of the neural network, no training of deep neural network. If even not even training even deep neural network with 2 layers, it was not getting trained properly. Forget about the neural network with more than 5 layers or 10 layers or 15 layers, right? So no training of a deep neural network, right? So, and this problem is called as vanishing gradient problem. This problem is occurring because of multiplying a lot of derivatives with these values, fractional values, right? So that's it for this video. We'll meet in the next video.